What is proposition? Proposition is a declarative sentence that is either true or false, but not both. For example, Amir is a boy. And second example is 1 plus 2 is 3. Sentences which are comments, question, exclamations are not proposition. For example, what time is it? And second example is what a beautiful butterfly. So, next, what is compound proposition? Compound proposition are formed from primitive proposition by using logical operators. The statement, it is not the case of P, is another proposition called the negation of P, denoted by negation P. For example, P, today will rain. Negation P, it is not the case that today will rain, or today will not rain. Logical connective. Logical connective is a logical constant that we use to connect two or more formula, such as two atomic formula P and Q. It is also called as logical operators. So, for example, type of statement, conjunction is and with symbol like this. Disconjunction or with symbol like this. Negation, not, with symbol like this. And implication, if, then, with a symbol of arrow. And the last one is biconditional, if and only if, with a symbol of two arrow. Okay, next, for conjunction, and, with a symbol like this. The conjunction of P and Q is the compound statement P and Q, denoted by P and Q. It is true only if both P and Q are true. For example, so the second one is this conjunction called or. The symbol is like this. The disconjunction of P and Q is the compound statement P or Q, denoted by P and or Q. It is true if at least one of P or Q is true. For example, so the third one is negation, which is not, with a symbol like this. The negation of a statement P is not P, denoted by negation P. Negation P is true when P is false. Fourth one is implication, if, then. The symbol is like an arrow. So, the statement if P then Q or P implies Q, denoted as P implies Q, is called conditional statement or implication. Statement P is called the hypothesis premise and Q is called the conclusion. P implies Q is false only if P is true and Q is false. For example, so the last one is biconditional, if and only if, with a symbol like a double arrow. If P implies Q or Q implies P, we write it as P if and only if Q, and read as P if and only if IFFQ. It is true when both P and Q have the same truth value. So, for the truth value, we have three. The first one is tautology. Tautology is a proposition that is always true when whatever the truth value of the component statement. So, the second truth value is contradiction. It is a proposition that is always false whatever the truth values of this component statement. So, the last truth value is contingency, a proposition that can be either true or false, depending on the truth values component statement.
Hello everyone, today we will be discussing the concept of logical equivalence in propositional logic. Compound propositions that have the same truth value in all possible cases are said to be logically equivalent. This is a fundamental concept for comparing statements. More formally, two propositions P and Q are called logically equivalent if the biconditional statement P, if and only if Q, is a tautology, meaning it is always true. The notation used to show this equivalent is either P biconditional Q or P equivalent Q, indicating that the true value for both P and Q are identical across all scenarios. The conclusion: understanding logical equivalence allows us to substitute one statement for another without changing the overall meaning or true value in an argument. As you can see here, to determine whether two propositions are logically equivalent, one of the most reliable methods is using a truth table. The propositions P and Q are logically equivalent if the columns in their truth table are identical. That means for every possible combination of true values, for the variable involved, both propositions yield the exact same final true value. We have three examples to walk through. Our first example demonstrates one of De Morgan's law, showing that the negation of a conjunction, negate P and Q, is logically equivalent to the disjunction of the negations, implies. We have three examples to walk through. Our first example demonstrates one of De Morgan's law, showing that the negation of a conjunction, negate P and Q, is logically equivalent to the disjunction of the negation, negate P or negate Q. We construct a truth table with column for the proposition P and Q. The conjunction P and Q, its negation negate P and Q. The individual negations negate P and negate Q. And finally, the disjunction negate P or negate Q. By filling out the table for all possible true value combinations of P and Q, we observe the resulting truth value for both complex expressions. The column for negate P and Q and negate P or negate Q are identical across all rows. Therefore, the two propositions are logically equivalent. The second example covers the other De Morgan's law, showing that the negation of a disjunction, negate R or S, is logically equivalent to the conjunction of the negations, negate R and negate S. Similar to the first example, we create a truth table with column for RS, R or S, negate R or S, negate R, negate S, and negate R and negate S. We complete the truth table to compare the outcome of both expressions. The column for negate R or S and negate R or negate S have the exact same true values in every scenario, proving they are logically equivalent. Our final example demonstrates that a conditional statement A implies B is logically equivalent to the disjunction of the negation of the antecedent and the consequent negate A or B. The truth table includes column for A, B, the conditional A implies B, the negation negate A, and the disjunction negate A or B. We fill in the true value to compare the result for A implies B and negate A or B. The column for A implies B and negate A or B are identical, confirming their logical equivalence. In summary, truth table provides a clear, systematic method for verifying logical equivalence by comparing the result truth values of different expressions across all possible scenarios.
Okay, the next one is logical implication. What is logical implication? Logical implication is a type of relationship between two statements or sentences. This relation translates verbally into logically implies or the logical connective if or then and is symbolized by a double line arrow pointing toward the right. In logic, implication is a relationship between different propositions is a logical consequences of the first. For instances, if A and B represent semantic statements, then AB means A implies B, or if A then B, the word implies is used in the strongest possible sense. How to write logical implication statements? An implication is based on the if this then that model. A typical statement use the following format: A implies B. Okay, for example 1, it asks us to show that P implies P or Q. So, to show that P implies P or Q is a tautology, we construct a truth table. For all possible true values of P and Q, the statements P or Q is true whenever P is true. When P is false, in implication P implies P or Q is always true, regardless of the value of P or Q. Therefore, the statements P implies P or Q is true in all cases. Hence, since P implies P or Q is tautology, then P implies P or Q. Okay, for example 2, it asks us to assume that P and R are false while Q and S are true. Find the true value of the propositions below. For A, since P is false, the negation of P is true. Since Q is true, the statement negation P implies Q is true. Next, since Q is true, the negation of Q is false. And because S is true, the statement negation Q or S is true. Since both sides of the biconditional are true, the whole statement is true. Therefore, the statement in A is true. And for B, since S is true, P is false, and R is false, the negation of R is true. However, P and negation R is false. So, the statement S implies P and negation R is false. Next, since P is false, the negation of P is true. Because R is false and Q is true, the statement of R or Q is true, and therefore negation P implies Q, R or Q is true. Since S is true, the entire second bracket is true. Finally, because the first bracket is false and the second bracket is true, the whole statement is false. Therefore, the statement in B is false.
Laws of logic. We can use logical equivalence to reduce complex formula into a simple one. In this part, we have some basic laws, such as identity laws. P and true is logically equivalent with P. P or false is logically equivalent with P. Next is domination laws. P or true is logically equivalent with true. P and false is logically equivalent with false. For example 1, we have equation where it gives us P or F and Q or T, which is F is false and T is true. By using identity law, we can prove that P or F is logically equivalent with P. So P or F get P. Next equation will be P and Q or T. Next, we can use domination law, where Q or T is logically equivalent with T. So, the next equation we will get P and T. Lastly, we can use the identity law, where it proves P and T is logically equivalent with T. So, the answer we will get. The other basic laws is double negation law, where not P is logically equivalent with P. Then, De Morgan's law, where not bracket P and Q is logically equivalent with not P or not Q. Not bracket P or Q is logically equivalent with not P and not Q. Other law is distribution law, where P and bracket Q or R is logically equivalent with P and Q or P and R. And P or bracket Q and R is logically equivalent with P or Q and P or R. Next is absorption laws, where P and bracket P or Q is logically equivalent with P. Then P or bracket P and Q is logically equivalent with. Next law is commutative law, where P and Q is logically equivalent with Q and P. And P or Q is logically equivalent with Q or P. Next law is associative law, where P and bracket Q and R is logically equivalent with P and Q and R. Other than that, inverse law is also the one of the basic laws, where P and not P is logically equivalent with false. P or not P is logically equivalent with true. Definition of implication, where P implies Q is logically equivalent with not P or Q. And definition of biconditional is when P if only if Q is logically equivalent with P implies Q and Q implies P. Let's take a look at example 2. First equation is not bracket not P and not Q. Using De Morgan's law, we will get not bracket not P and not Q is logically equivalent with not P or not Q. For the next equation, we will get not P or not Q. By this equation, we can use double negation law, where not P is logically equivalent with P and not Q is logically equivalent with Q. So the answer is P or Q. Next example is equation not P or F and not Q. In this equation, we can use two laws, such as double negation law, where not P is logically equivalent with P and not Q is logically equivalent with Q. Next is identity law, where P or F is logically equivalent with P. So the next equation we will get is P or Q and Q. In this equation, we can use absorption law, where P and Q is logically equivalent with P. So the next equation we'll get is P or P and Q. In this equation also, we can use absorption law too, where we will get P or P and Q is logically equivalent with P. So the example is example 3, where the question given is to show not P and Q is logically equivalent to not P and Q. The equation not P and Q, we can use De Morgan's law, where not P and Q is logically equivalent to not P or not Q. Then the second equation we'll get is not P or not Q and Q. In this equation, we can use distributive law, where not P or not Q and Q is logically equivalent to Q and not P or Q and not Q. So we will get Q and not P or Q and not Q. Q and not Q is logically equivalent to false, where the inverse law is used. Then we will get Q and not P or false. In this equation, we can use identity law, where Q and not P or P is logically equivalent to Q and not P. So the answer we'll get is Q and not P. So that means not P and Q is logically equivalent to not P and Q.
What is a mathematical statement? A mathematical statement is a sentence that can be classified as true or false. For example, first, a straight line either intersects another line at exactly one point or they are parallel. The sentence is true. Second, 5 plus 2 equal to 105 plus 2 equal to 105 plus 2 equal 10. The sentence is false. 7 minus x equal to 47 minus x equal to 47 minus x equal to 4. Depends on x could be true or false. Fourth, the number x is greater than 0. Depend on x. And lastly, there is a real number theta such that the cosine of theta equals to 1. The sentence is true. So, what exactly is a mathematical proof? A mathematical proof is a logical argument that demonstrates a statement is always true. It archives this using established rule of logic, clear definitions, and known accepted mathematical result. A key component of many proofs involve conditional statements, which take the form if A then B, written symbolically as A implies B. A is the assumption or hypothesis, B is the result or conclusion. To show what a statement A implies B is valid, we must prove that the conclusion B must be true whenever the assumption A is true.
So next is mathematical terminology and construction method. So let's begin with the definition. A mathematical definition is an agreement among mathematicians about the meaning of a term. In simple words, it clearly explains what a concept means so everyone understands it in the same way. You can think of it as a shortcut that represents a bigger. Now look at some important terminology. First is proposition. A proposition is a statement that is either true or false. It is something that we usually try to prove. Next is theorem. Theorem is also a proposition, but it is considered very important because it has significant impact or wide application. Then we have lemma. A lemma is like a helper statement. It is proved first, then used to help prove a theorem. After that, a corollary. A corollary is a statement that follows almost immediately once a theorem is proven. In other words, if the theorem is true, then the corollary must also be true. Next is an axiom. An axiom is a statement that we accept as true without proof. These are basic assumptions that form the foundation of mathematics. Finally, let's talk about implication. Write as A implies B or A arrow B. This can be read in several ways, such as if A then B, B follows from A is sufficient for B is necessary for A only if B. All these sentences mean the same things, just expressed differently. Now, let's move on to the construction method. The construction method is used when the conclusion contains an additional statement, meaning it says there exists, there is, or such as. Symbolically, we often see words like there exists or the symbol extensional. We use this method when the conclusions say that an object exists with a certain property and that something happens to the object. There are three main steps in construction method. Step 1 is identify the object, the certain property, and what happens to the object. Then construct the object. Here, we usually use the given hypothesis to guess or build the object. Sometimes that involves creating a formula or choosing a suitable value. Step 3 is show the constructed object has the required property and satisfies the condition given in the conclusion. Now let's look at the example 1. The statement is there is an integer p greater than 2 such that p squared minus 5p plus x equals to 0. First, we identify the components. The object is integer p. The certain property is p more than 2. That something happened part is equation p squared minus p minus 5p plus 6 equals to 0. This step is very important because if we cannot correctly identify this three part, we cannot apply the construction method properly. Now let's look at the example 1. The statement is there is an integer p greater than 2 such that p squared minus 5p plus x equals to 0. First, we identify the components. The object is integer p. The certain property is p more than 2. That something happened part is equation p squared minus p minus 5p plus 6 equals to 0. This step is very important because if we cannot correctly identify this three part, we cannot apply the construction method properly. Moving to the next question, example 2. The statement says that if two numbers s and t are the rational number and their sum is also rational number. So first, let's identify the hypothesis and the conclusion. The hypothesis tells us that s and t are rational number. The conclusion tells us that if the sum of s and t is rational number, since the conclusion involves showing the existence of a certain form, we will use the construction method. Next, we recall definition of rational number. From the hypothesis, because s and t are rational number, we can express each of the terms as a ratio of two integers with non-denominators. Now, we construct the sum of s and t. When we add two ratios and simplify, the result can again be written as a ratio of two integers with a denominator that is not 0. This shows that the sum of s and t satisfies the definition of rational number. So, for the last, we write the condensed proof. From the hypothesis, since s and t are rational number, by definition, they can be expressed as ratio of integers with 0 denominators. By construction, their sum can also be written as ratio of two integers with a non-zero denominator. Therefore, the sum of two rational numbers is rational.
The conclusion is mathematical logic provides a fundamental framework for understanding and analyzing statements using precise rules and symbols. Through the study of logical connective, logical equivalence, and law of logics, we are able to simplify and evaluate complex propositions accurately. Logical implications helps us understand conditional relationships between statements, while proper terminology and construction methods ensure clear and valid reasoning. Overall, this topic strengthens logical thinking and forms the foundation for problem solving in mathematics and other related fields. Thank you.